All right. I want to tell you a story about my favorite controversy in lambda CDM theory. So what we know from lambda CDM is that all dark matter halos are surrounded by a swarm of rapidly disintegrating satellites, and they're surrounding dark matter components, dark matter subhalos. The controversy is that despite the fact that this is a very well-explored subject, there is a subset of theorists who currently believe that our ability to understand what lambda CDM actually predicts these subhalos are doing is not as good as traditional modeling usually assumes. So there's a lot of characters that play a role in this story, and I'm going to focus on one of them. And it's an admittedly somewhat technical one. It is a tool known as a halo finder. So this is a program that you run on a simulation output, and it tries to tell you what all the subhalos are. And it turns out that this tool is sort of very complicated to write. It's trying to do a very difficult job. And because of that, there are certain biases that can come into our analysis. So this is what my conclusion slide is going to be. I'm going to conclude three things. So first, I'm going to conclude that our understanding of how accurate subhalo finders are is poorly understood. I'm going to conclude that we've developed a new subhalo finder, and we've developed a new testing system which, in my personal opinion, actually resolves that first point, if you follow all the steps in it. And then lastly, we conclude that on the test that we performed, our subhalo finder substantially outperforms the other finders that we tested. I'm going to note that this S is intentional, but I'm only going to show you one halo finder that I'm comparing against for political reasons. So in order for me to conclude these three things, there are three arguments that I essentially need to make to you. So first off, I need to argue that this first point is at least plausible. You don't have to be convinced during the plausibility argument, but you at least have to hopefully buy that this is not a crazy thing to think might be true. So the second thing is I'm going to have to introduce what our subhalo finder is. It's named SimFind. This is a reference to another subhalo finder called SubFind, but they are very different things. And then finally, I'm going to have to describe a little bit about the system that I described for testing. So I'm going to focus on one aspect, but there are many. So one last housekeeping thing. Throughout this talk, I'm going to show pictures that I've taken of cats at the Palo Alto Animal Shelter. In addition to being cute, these are a sign. These are a sign that I don't actually care if you read the plots on this slide. The things that I'm showing on cat slides are illustrations of large bodies of work that I'm summarizing. We're not intended to instantly absorb all the stuff that's on those slides. So let's get to our first cat slide. So I think the crux of this controversy, you can sort of argue for it in many ways. This is what I think is sort of the most compelling. If you look at cosmological simulations, subhalos appear to be very fragile. And if you look at idealized simulations, like Barry was showing us yesterday, they appear to be very durable. In fact, many people have argued that they're essentially indestructible in idealized simulations, but I think that's probably not true. So as an illustration that, again, you don't need to absorb fully, deep within the bowels of the appendices of the Universe Machine Methods paper, Peter Baruzzi demonstrated that even at very high resolutions, subhalos were dropping out of the catalog after having lost a relatively modest amount of mass. And then when you go and you sort of look at the idealized literature, there's no way that you would be predicting that these things are truly disrupting in some meaningful way at these sorts of masses. Now, there are two reactions that you can have to having a conflict like this. So one is my reaction, which was abject horror the first time that I learned about these simulations. The other is to say, well, hold on, let's calm down. We've done tests on these full cosmological simulations. And I want to summarize what I think are the two most compelling versions of those tests. So this is no longer a cat slide. I actually do want you to read this plot. What this is this is a mass function. So the x-axis is showing you the ratio between subhalo masses and host halo masses. And the y-axis is showing you the count. And what most of the curves here are different subhalo finders. And the only thing that you're supposed to take away from this plot is that those lines are close together. And the argument goes, well, if they were wrong, why would they all be wrong in kind of the same way? And that's a compelling argument. But note that it's not actually a proof. They could all be wrong. And the other thing is this is actually a very fragile argument. All it takes is one subhalo finder that you find credible, which is predicting more than this, and suddenly this test isn't telling you anything anymore. The other class of test that's very popular is what's known as a convergence test, where you compare different resolutions. So this is a mass function again. I only want you to look at the red curves. So this is for a particularly popular subhalo finder named Rockstar. It's the one I'm going to be comparing against for the rest of the talk. The solid line is showing the mass function in a high-resolution simulation, and the dashed line is showing it in a low-resolution simulation. And again, the only thing that you're supposed to read out of this is that that dashed line and that solid line are almost the same. And so the argument goes, well, subhalo finders should get better as you get more and more resolution. And we've reached the limit where improving the resolution actually helps us find more subhalos. Again, this is a compelling argument, but it's not perfect. So there's something known as false convergence. If you want to see an example of that, I have an earlier paper where we showed this happened in the multi-dark concentration mass relation at low masses. But also more generally, this argument only holds if the main reason that subhalo finders aren't finding subhalos is due to lack of resolution. And we know that this isn't true because they can lose track of subhalos just because the phase space distribution is really complicated. But this kind of leaves us at an impasse. So on one hand, we have a priori arguments that we expect these things to be durable. On the other hand, we have two good but not perfect tests that are telling us that the simulations that say that they're fragile are reliable. So, and my approach to this is that I think that these tests are, in fact, imperfect in exactly the ways that I've hinted at in this introduction. So, onto the scene comes our next character, which is my subhalo finder that I've been writing called SimFind. Now, this is normally the part where I would describe in great gory detail how all these things work. I actually think this is not a productive use of anybody's time. So for those of you who are familiar with subhalo finders, this is what's known as a particle tracking subhalo finder. It is somewhat similar to things like HPT Plus and Sparta, but it makes so many decisions that are different that there's really no point in sort of comparing them at that level. The thing that is more relevant is this plot right here. So what I'm showing you here is a very typical subhalo from one of our simulations. Time is on the x-axis, and the y-axis is the distance between the subhalo and its host. And the dashed black line is the radius of the host. So what happens, one last thing. So blue right here, SimFind. Red is Rockstar, our comparison subhalo. And so what happens is it comes in, pericenter, apicenter, and boom, Rockstar loses track of it. And SimFind keeps on going, many, many more orbits like this. And if you go and you pull out the particles associated with this subhalo in the simulation, you find that it looks like a subhalo. There's a bound clump with thousands of particles with coherent motion that still contains the most bound particles at the time of infall. And if you are kind of psychotic like me, you might say, well, I'm going to go do this for 1,000 other subhalos and see if they all make sense. And they don't all make sense, but about 90-something% of them do, 99, 97, somewhere in that range. So that's pretty cool. Now, the next thing that's relevant is let's look back at those mass functions again. So I want you to start by looking at the red lines, and I'll walk you through the rest of this plot. So again, this is our favorite plot, a mass function. The solid red curve is showing you the mass function that we measure from SimFind. This is a little bit different than one of the earlier mass functions. This is actually infall mass, but that only sort of changes things qualitatively. And the dashed line is showing what you recover from Rockstar. And in the bottom panel, the one that you really want to focus on, you're seeing the ratio between these two mass functions. And what we see is that for all the subhalos in the host halo, there's about a 30% offset at low resolutions, and as you go to higher resolutions, you're finding more and more. It can get up to a factor of 100%. And then as you get closer and closer to the center of the halo, which is what those colors are, so blue is a sphere that's very close to the center of the halo, the number of extra subhalos that you find increases even more. And additionally, we find that as we put more resolution into these simulations, we keep finding more subhalos. And when we look at those subhalos, they are real subhalos. They're not fake detritus that we're sort of finding. Now, we could stop here, but instead we sort of added a test framework on top of this that allows us to make more quantitative statements. Now, I would sort of love to go through all the different parts of this, but instead I'm going to focus on just one right here. But just sort of know that any subhalo finder can kind of wiggle its way out of looking good on one or two of these tests. You really need to sort of look at all of them. And that's to measure the disruption masses. So these are the masses at which these subhalos are falling out of the catalog. It's analogous to what Peter was doing in his universe machine appendix. How much time? Wonderful. So then we are going to skip some interesting statistical insights and talk right about this plot. So this right here is the CDF of disruption masses. So what we're seeing on the x-axis is the ratio of the mass at which the halo finder loses track of the subhalo to what its infall mass was. In blue, I'm showing the results for SimFind, and in red, I'm showing the results for Rockstar. And this is for a high-resolution set of halos, so these are about 100,000 particles, the point where like most people are like, it doesn't really matter what numerical problems you have, these will be fine. And what we see is that there's about an order and a magnitude and a half difference between what SimFind and Rockstar are are sort of predicting as the disruption masses. Now, the next thing that you can do is you can ask how this works as a function of resolution. And this is the thought that made me shout in the middle of the sort of Slack lounge when I saw it, and the grad students made fun of me. So what each of these lines here, they're different quantile from these cumulative distributions. And blue is Simfine and red is Rockstar. And what you see is that Simfine, as you're increasing resolution, is finding more, is tracking subhalos for longer and longer periods of time. But with Rockstar, increasing resolution does not improve the survival masses. And the reason is that Rockstar is not resolution limited. It is limited by phase space distributions that it cannot deal with, that are too complicated for it to figure out. And what that means is that as you do those convergence tests where you are increasing the resolution, you aren't changing the distribution of disruption masses, and so your mass function stays the same. And that's why you can do these resolution tests without sort of seeing any sort of issue. And so this is sort of the conclusion that we get from this shard of the test rainbow, which is that we can track these things down to orders of magnitude lower masses. I will just briefly sprinkle some other tidbits from these tests in case they interest people. So for example, we can replicate the tidal tracks and very pessimistic convergence requirements that are suggested by idealized simulations, some of them, but not all of them. We've identified a new class of problem in orphan models that for certain classes of models basically makes them make predictions that are so inaccurate that it's not useful. We demonstrated that when you combine this with the disruption masses, our subhalo finder can track subhalos to the point when a galaxy would usually disrupt, which is not true for something like Rockstar. And we identified a number of as yet unresolved merger tree issues, which form a really big problem for codes like ours. So I'll leave us up here with the conclusions. The code is not yet public unless you ask me very nicely, but the data catalogs are public, and I'd be happy to help you use them and give you advice on them.
Questions?
Nice work. You briefly mentioned the similarity with HBT. I'm curious about how HBT performs for this benchmark.
So I promised Josh and Hans specifically that I would not answer that question because I haven't done enough testing to really convince myself that I know the answer. What I will say is I do have subroutines inside of this that, in my opinion, completely emulate HBT+, and I know the properties of those very well. But Joshin has been burned in the past by people claiming that they've been re-implementing HBT+ and not actually doing it. So I'm waiting to make any strong statements. You may want to draw conclusions from the fact that HBT+ agrees with other subhalo finders on some tests, but you may also criticize how sensitive those tests are to these sorts of issues.
I see.
Okay.
Yeah, thank you. And I have a quick comment is that you mentioned the artificial disruption in cosmological simulations. We are preparing a paper which will come soon. We found that actually artificial disruption is not a real problem in cosmological simulations for subhalos above like 200 particles, because the main disruption channel is actually due to major mergers in the high order subhalos.
Oh, this is actually a really important point that I disregarded. Major mergers are a totally different story. All of these things have low enough mass ratios that there is not sort of the characteristic major merger.
Yeah, that's why they are very different from the behavior of idealized simulations.
That's a really important clarification. So basically, just in case people aren't familiar with this, there's basically two modes that subhalos merge with. So if you have a low mass ratio, you're like 1/10 of your host mass, you just orbit with this very weak dynamical friction essentially forever. If you're bigger than that, there are new dynamical friction channels which cause you to get destroyed in like an orbit. So it's qualitatively different, and you do have to care about that. So thank you for that clarification.
While the next speaker sets up, we can have a very quick question.
So you mentioned that this works in 97 to 99% of the cases.
Yeah.
When does it not work?
So the thing you need to understand about subhalos is that they are the most miserable things you could ever try to analyze. There are so many special cases. There's so much nonsense. Like one thing I didn't talk about is how you deal with subhalos and subhalos. it's actually very easy for you to convince yourself that the central halo in a halo-subhalo system is the secondary, the smaller halo. There's a lot of but the number of downtime I'd love to get that number lower.
All right, let's thank our speaker again.